presentation with Ernesto. Ernesto, welcome. Ernesto's presentation is applied telemetry to security automation and IPv6 networks, and we have two co-authors, Ernesto, who is with us here, and Henry Alves de Godoy, who is online through Zoom. Ernesto, you have the floor. Thank you. Good morning. Good morning. Good morning, everyone. And thank you, Carlos. And thank you to the program committee for accepting joint work with Ernesto, representing the Catholic University of Salta, and with UNICAMP. This work that we're going to share with you is a result of a joint research that we carried out, a partnership that was very interesting, that we have had now for 2 years together with Ernesto. So I would like to thank for this partnership. I'd like to thank LACNIC as well for supporting this project, which is very important. And this brings together the academy and the researchers and all those who, so these presentations have been very interesting, and the partnership with the Academy and LACNIC. So today what we're going to do is to speak about applied telemetry with automation in networks. So the purpose of the presentation is to show how more modern telemetry technologies not only allow to carry out monitoring, but also to provide the security, which is a focus of the presentation. This is something that we consider is essential for future networks and based on IPv6. So can I have the next slide? Ernesto, can we have the next slide? Yes, that one precisely. So in this screen, we start to understand the development of network management. In the past, we used traditional tools like SNMP, as Carlos just mentioned. Edwin's presentation was most interesting and has a lot to do with the work we are doing. We all are familiar with SNMP. We have known this for some time now. We all started to use SNMP as a customer, as a CLI that is executing in Linux, and also using the tools to collect in SNMP. So this worked quite well. We nowadays use it, but there were nevertheless limitations. There was limited scalability. There was a dependency on non-structured formats. So we realized that there were major difficulties in there was low interoperability between devices from different vendors. Today we have different difficulties. We must also refer to the RPC protocols. All these things are based on standard models, which today enable a more advanced automation, connection in real time, integration with several orchestrators, in addition to monitoring options. This is quite interesting. This is a table comparing traditional and modern technologies. We cannot compare absolutely everything, but we see the traditional technologies that were based on, for example, we always had to ask the devices what they were doing, so we received limited amount of data. And we had quite a lot of difficulties. The way technology works today is quite different. So the devices themselves send information at the same time. So now the data format is JSON and protobuf and others. For example, these are more modern types of technologies. All this has facilitated the work with the vendors. Over here we have the different devices with active automation. As a result of this technological leap, we have the concept of network telemetry framework. RFC 9232 refers to this, to telemetry. So telemetry is a bit more than just monitoring. In addition to collecting and generating and analyzing data, show the status and performance of the network in real time. This telemetry allows us to detect and prevent intrusions. We can identify anomalies, malicious events. It allows to do ongoing verification of the network policies. We can monitor in real time the defined metrics and the service contracts. There's load balancing and traffic engineering. So in other words, we went from a traditional reactive model and also limited through the SNMP, and we went over to a more proactive model, which is much more intelligent. In this slide, we show the security automation of IPv6 networks. So we connect all the things we have been doing over the past years together with Ernesto. And we're quite surprised about the possibility that GNMI provides for the purpose of carrying out simulations. Ernesto will show you in a while an example with a light container and with simulations what you can do. In the past, we used to have tools that were in charge of doing monitoring, which were quite complex tools for the purpose of the deployment. They were quite limited in terms of the visualization. So what we're now sharing with you are the results of our studies. Now we have more modern protocols, as I commented already. The objective is to develop a GNMI-based system and also automation in IPv6 security.
This means many things, such as, for instance, detecting the possibility of detecting hosts in the network automatically, and to identify unknown devices and to apply security policies in real time, and even to create ACLs mitigating any attacks or the various attacks that we have been studying and that we are monitoring. That is, we are evolving with this work, starting from an annual to an automated and efficient model that integrates the network operations. So in the next slide, I'm going to give the floor to Ernesto, and he'll continue to discuss the virtualized network topology, and he's going to go on with the presentation. Thank you, everyone. Well, this slide shows us the topology I virtualized at a container lab. You see the telemetry stack formed by Prometheus to collect the meters in a database, to visualize it in Grafana, and then the aspect search. Because I'm going to show it now, I need to see bindings, valid bindings of MAC address, port, IPv6, global, unicast, link local, to later on apply those ACLs in a Nokia SR Linux device. Very briefly, what is the topology, what are the versions, and what did I have to create. The version of the device. In this case, I configured it for it to work as a layer 2 device, as a switch. It's Nokia SRL Linux version 24.10. I had to configure a collector module based on GNMI client with the GNMI client, Python, and Scapy, because the brain of the entire thing is this new collector. Not only does it receive subscription of the metrics, but it's the one that will correlate the information it receives from the Nokia device to put together the valid um, to apply the CLs in real time. Prometheus and Grafana, based on a Nokia developed schema for a telemetry lab. And finally, the hosts that I had to create by installing the tools, the audit tools of Fernando Gont, THC, and the other alternative THC IPv6 toolkit. Now, how does it work? What's the process like? Well, in step one, the new collector receives the metrics of the changes in the MAC address table of the device. So whenever a node is connected, it will receive an update. And the screenshot of MAC address and port. And the next step, but simultaneously, it's capturing traffic in the process of neighbor discovery protocol, specifically in duplicate address detection. In this process, I manage I get the MAC address to the IPv6 link local and the global unicast. So with this information, I put together a file, an extension JSON, a script with no binding, but putting together the valid bindings. And simultaneously, I sent to apply the ACLs to the Nokia device and Elasticsearch to visualize and to check that valid binding is correct. So here, this is the main functionality. So I receive these metrics, and in the on-change, in the and the script, this does a capture and the traffic in the Slack process. It could be perfectly well in DHCP-v6 just by changing it. It correlates the traffic, and it obtains with the data that it gets from the MAC update file. It generates an output file that is called MAC IPv6 binding dynamic.json. It generates the ACLs, and I send it for Elasticsearch for visualization. And then what do I need to know? Well, really, when do these ACLs get applied? Plus, for instance, consumption of CPU. How much does it cost that to apply those ACLs? Or, for instance, I want to know multicast traffic if there's a flooding attack or something. These two scripts, capture bindings, were generated with the assistance of AI. At the beginning, I used it natural, and I said, but why don't we put together a methodologic framework for the use of AI? So I defined it as a number of phases or steps, saying, well, let's identify the problem. What do I need to do? Apply security based on automation. by using GNMI. Then we had the solution and breakdown architecture. I need the scripts, I need the capture, I need to subscribe the metrics. And it is in phase two that, with the assistance of AI and the prompts, uh, I said, well, with prompt engineering, let's generate the scripts. What do I need? As any developer, I need to have an in-depth knowledge of how the protocol works. If I don't know how NDP, neighbor discovery, works, I can't ask AI to generate a script, and even less so to validate them and to check them. Because really, and to really see that they work. So that is phase three, validation and control. So this test applies to ACL and it does it efficiently. That is essential and it's robust. So you find this perfectly well, all the codes, all the configurations in a GitHub repository. So I don't want to dwell on this in depth, but it gives you an example how the output of this file transforms into ACLs using the Yank model proposed by Nokia. And it's a standard that you can apply with other vendors. The metrics. This is a brief code example also using the Yank model and show how that is exported to Prometheus and Grafana. Other useful metrics, as I just said, subscription to statistics of multicast traffic and CPU consumption. And now I'm going to show you a video showing how the solution works because that's an interesting thing. From the beginning, please. Maybe they could adjust the volume. Well, let me start with the topology already deployed. All the scripts are integrated in the D supervisor, and from now on, I'm already capturing traffic and I'm receiving the metrics of the MAC address table. So how do I mimic a connection with the network with a config hd1 doni app command? And from then on, the device learns what hosts are connected to each port. Simultaneously, the auto configuration of IPv6 address is being configured through Slack. Notice that I do it for the host PC1, PC2, PC4, those devices, and the script that it captures is already correlating and sending those valid bytes. Notice that I can see time mark the interface, that the switch to which the host is connected, the IPv6 global address, link local, and the MAC address, what we know as NDP snooping, neighbor discovery snooping. In just a matter of seconds, it will learn the other hosts that will join. And the interesting thing here is that it's dynamic. If I do discovery up, config up, it will learn the new configuration because the script supports when the host is configured to generate temporary IPv6 addresses. So it would have to generate other binding for the other IP that auto-configures the device automatically. I'm already receiving the metrics of the ACLs and the metrics of multicast traffic for each port in the device switch. What I'm going to do now is to generate an example of an attack, flooding attack, with origin IPs, random and false, and that needs to be mitigated. Here we have an example documented. Here you have a 80K flood advertised. In this case, this is a flooding of neighbor advertisement. Obviously, the attack is mitigated because I just said I have configured ACLs only to allow valid traffic from the addresses it learned when the node connected to the network. So if the attack generates with random source IPs and it needs to be mitigated, there you can see in the dashboard the number of packets that were dropped. And I visualize that the rule really applies. The solution that was proposed also contemplates the case that if an attacker has access to a host that has a legitimate IP, it can start a flooding attack. In this case, it's a router solicitation. It uses the same IP of origin. The previous ACL doesn't apply because it's a legitimate ACL. However, I can visualize the attack as a multicast traffic flooding, and automatically I see it here in this dashboard. The number of metrics that I receive from the device through GNMI and the number of packets that apply, the packets per second that you send to a multicast address. And applying all the studies that we conducted earlier that we showed in the last LACNIC, considerations for filtering NFSP version 6, I also applied the ScanNet rules. Here you have an example of local scanning. And this is mitigated too. And I visualized that I mitigated the attack, or the attack was mitigated actually. So, as I just said, this is a solution that I've enhanced. Not only does it support standard privacy addresses, but it also supports temporary addresses.
This is automatic in the sense of the learning process and the application of the ACLs. So we will be wrapping up now. I'll go over to the conclusions. The obtained results show that the adoption of a telemetry standard based on these protocols significantly improves the detection capacity, the response, and the early mitigation in view of potential attacks. Like Henry said when we started, the possibility of not reacting, of course, with yesterday's news, but we need to react proactively. So this approach not only provides support for visualization and ongoing monitoring of the status of the network, but it also enables dynamic automation in the application of traffic filtering rules. This interoperability, real interoperability, can be achieved only once the vendors adopt common data models. I did tests with Arista, I did tests with Cisco, and although it is quite true, each uses the proprietary models, but simply knowing how the data model is, we can then automate and modify the script to apply these rules. Here we have the references of all the things that I used, and at the end you have the link to the GitHub repository with all the information for the container labs. Thank you very much. Thank you, Ernesto. Great presentations. All this section on telemetry and monitoring was great. I think there's a whole issue, a whole area to try and solve in the sense of network and monitoring. We have time for questions. One question, two questions if you're brief, and otherwise, okay, we can have the coffee break now and continue with the conversations in the trade show. Thank you. Henry, are you still there? And with this, we close the first slot, the first LACNOG slot, and we meet again at 11:30 after the break. Thank you.